Okay, this is the lecture 13 of Data Communications and Network 1. This is on Chapter 6, Data Link Control Protocols, Part 2, which is the high-level data link control. Okay, so let's look at the sheet. HDLC, high-level data link control. This is our two-way communications. Okay, this used to be the most important data link control. Okay, it's widely used in the standard, and it's basic for other data link control protocols. Okay, but it's quite old. This one, they have the basic characteristic is that there are three station types, because in the past the computers are expensive, right? They were expensive, so they would have a different like primary station and secondary station. So we have like a server and a terminal, which is different cost. Okay, right now we usually have like the same, the same, not terminal and server, but just a computer. Okay. Anyway, the primary station will control the operation of the link, and it will issue commands to the secondary station. The secondary station will work under control of the primary station, like the terminal in the past, and it issue response to the command of the primary station. The third one is the combined station, which is more like what we use today. Combine the features of both primary and secondary stations, so it may issue both commands and response. So it's kind of peer-to-peer, the same level. Okay. For the link configuration, we have unbalanced and balanced, okay, configuration. The unbalanced configuration is that one primary and one or more secondary stations, like when you have server and a lot of basic computer like a terminal doesn't have a lot of features. Okay, that is unbalanced. For the balance, you have two combined stations, so the station that is like equal, okay, like what we use today. The data transfer mode, there are three data transfer modes. Okay, the normal response mode, or NRM. This is unbalanced configuration. Okay, and the secondary may only transmit data in response to a command from the primary. So this is, as I say, in the past. Okay, that usually has a main computer and many terminals. The second one is the asynchronous balance mode, or ARM. In this case, this is a balanced configuration. In this case, either combined station can initiate the transmission. The third one is asynchronous response mode. Okay, this is also an unbalanced configuration. Okay, but secondary can initiate the transmission. Okay, this is the frame format, the frame structure. You can see that this frame structure, okay, include flags. Okay, flag and 8 bits of flag, and address is also 8 bits, but it can be extendable to 1 byte, 2 byte, 3 byte, 4 byte. Okay, whatever long that you want, and there are control bits. Okay, which are 8 bits or 16 bit. Okay, and there are information bits that are variable. So any length that you want, and have a frame check sequence which is set to 16 or 32 bits. Okay, and last is a flag, again 8 bits, the same flag, okay, on the beginning and at the end. Okay, the extended address field, you can see that the address, okay, will the first set of address, okay, start with 0. Okay, and if this is not the last byte of the address, it always start with 0, and the last byte will start with 1. So if you have only 1 byte address, if you have 1 byte, okay, it will start with 1. Okay, but if you have address 2 byte, okay, it will start with 0, and then the next one will start with 1. Okay, the next byte will start with 1. If you have more than one byte, the first will start with 0, all 0, and then the last one will start with 1. Okay, n byte address So this is how you can extend the address field. Next is the 8-bit control field format. Okay. In this case, you have there are three formats, okay, of the frame. The first one is IFrame, information frame. The second one is supervisory frame, and the third one is unnumbered frame. For the IFrame, we will start the first bit as 0. So if the first bit of the control field is 0, you know that this is information frame. If the first bit is 0, then the next 3 bits are send sequence number. Okay. See, send sequence number, NS, okay, and NR is receive sequence number. So this is send sequence number, and then bit number 5 is called poll or final. Okay, we will talk about this in a little bit, poll and final. Then the last 3 bits are receive sequence number or NR. Okay, so this is two-way communications. The second structure is supervisory frame. In this case, it will start with 1, and the second bit will be 0. So 1, 0 is the beginning of the supervisory frame. Then bit number 3 and number 4 is S, which is supervisory function bit. Okay. Supervisory function bit has 4 different cases. Okay. Which is okay, here, this is supervisory function bit. If it's 0, 0 is receive ready. If it's 0, 1 is reject. If it's 1, 0 is receive not ready, INR, or if it's 1, 1 is selective reject. Okay, so this is the S, the meaning of the S to S bits here. And you have poll and final at the 5th bit, and the last 3 bits are also receive sequence. This is receive sequence number. So supervisory frame you send as an acknowledgement back, okay, when you don't have any data to send back to, suppose you are B and you don't have data to send to A, you send a supervisory frame. But if A has data to send to B, it have to send information frame. The last frame structure is called unnumbered frame. Okay, you have an MM is a number function bit. Okay, we will see in a little bit, and the first 2 bits are 1, 1. Okay, so if you see 1, 1, you know that this is unnumbered bit. This is to use as the start and beginning, and the beginning and the end of the transmission. Okay, this is not sending information and not sending acknowledgement. Okay, so this is M, unnumbered function bits, and P/F is poll final bit. Okay, now if you have, if instead of 8 bits control, if you use 16-bit control field format, okay, we have to extend this in order to use higher numbers of sequence numbers. Because if you use, in this case, for 8-bit control field format, NS have only 3 bits, okay? So it's like the B equals to 3 bits, so you have a window size no more than 7. But if you want no more than 7 for the go back in, okay? But if you want to use higher, larger window, okay, you use NS equal to 7 bit here, and NR also equal to 7 bit. So you extend the control field format of the control field into 16 bit, okay? In this case, you can use for go back in the B equal less than or equal to 2 to the 7 minus 1, so 127 frame, okay? In the window size is 127. The supervisory frame is NR is the same, extended to 7 bit, okay? But for the first 8 bits, we just patch 0, okay, after S, because S has only two bits. Now let's talk about the flag fields, okay? Usually we use a unique pattern, okay, of 0 and then 6 ones next to each other, and then 0. So start with 0 and end with 0. In the middle are 1s, okay? So you have 6 bits, and beginning and end are 0s. Okay. So if you see this pattern, you know that this is the beginning of the frame. So receiver on both sides are looking for this flag. That this is the start, when you start, and then the next one is the end, and then the start, and then the end, something like this. However, since you cannot control, okay, the data, so the pattern may appear inside of the information frame. Okay, so how do you do? How do you prevent, okay, this pattern to appear at the other position? Okay, that is not intended for the flag. Because if it appears in the information field, for example, you will think that this is the end of the frame, which is wrong. Okay, so this will destroy the frame synchronization if this pattern appear inside of the information frame. So to avoid this, okay, you use bit stuffing. Bit stuffing means that you add an extra 0 bit, okay, one extra 0 bit after a sequence of 5 consecutive ones. So you have 5, 1, 1, 1, 1, 1, okay? Then you add 0 always, okay? You add 1, 0. If it is not a flag, you always add 0. And at the receiver, if a sequence of 5 consecutive ones appears, so you have 1, 1, 1, 1, 1, then the next one 0, then the receiver will take the 0, that 0 out because it knows that this is not the data, this is the bit stuffing that the transmitters put in, okay, so that it will not appear as a, it will prevent the appearance of the pattern as a flag, okay. So if you checked, okay, and you got that this pattern 0 at the end, 0 at the beginning, and in the middle 6, 1, okay, it means that it definitely is a flag. But the weak point is that 1 bit error, okay, can merge or divide a frame. If you have an original pattern like this, and after bit stuffing you add, okay, so you don't have a problem of the bit stuffing technique, okay, you add zeros at the after 5, 1, so you never have a problem of the flag. However, if there is one error, okay, it's possible to change the pattern, okay, that you avoid into the flag pattern, or it's possible to change the flag pattern in another pattern. For example, if you have a flag, like this, okay, you have a flag, and then there's some error here, 1 bit error, so you receive something like this. Okay, so you think that this is not a flag. Send a flag, think not a flag. So wrong, okay, so that's a problem if there is even one bit of error. The address field I already talked about, okay, so if it's the last octet or the last byte of the address field, it starts with 1. If it's not, it starts with 0. If you want to broadcast to all stations, you use address of all 1. How about now the next one is control field. The control field is to identify one of the 3 frame types, whether it's IFrame or S-frame or U-frame, okay? So the information frame or IFrame will carry the data with ARQ piggybacking, okay? So you send both the data and the ARQ information in the same frame. You use 3 or 7-bit sequence number. For the supervisory frame or S-frame, it's used for fraud and error control, okay? You provide ARQ mechanism when you don't have any data to send. Again, using 3 or 7 sequence number. And there are 4 types of S-frame as I already told you. Okay, so RR receive ready is the same as ACK, okay? So, so use an ACK to act an IFrame where you don't have any data to send back. INR receive not ready, acknowledge all frames up to, for example, INR 3 receive correctly up until frame number 2, but not ready to receive frame number 3, something like that. Reject and selective reject is the same as what we have seen before. For unnumbered frame, it provides supplementary link control functions. Have examples of the basic functions is like mode setting, initialization, disconnection, and the 4th and final bit in the control field format. Okay, if you want to command in a command frame that you send from the primary station, you call this bit a poll bit. Okay, if you set to 1, means that you want to poll a response frame from the other end, because maybe something is wrong. Okay, you wait for a long time, you didn't get any response, so the primary can send the poll bit, okay, set to 1, and to ask for a response. Okay, and in the response frame that the receiver sent back, okay, it will call final bit. Okay, and if this set to 1 to tell that this is a response to the command, okay, that is asking the status. We will see an example of this in a little bit too. Okay, information field appear already in IFrame and Uframe and some of Uframe. Variable length, okay, but might be multiples of 8 bits, so it have to be in like bytes. Okay, the frame check sequence is error detecting code. Okay, error detecting or error correcting code. It calculates from the remaining bits of the frame, okay, except the flags. So it calculates from everything, but not include the flag. And the normal code is 16-bit CRC CCITT. Okay. The operation of the data link control protocol of HDLC consists of 3 phases. Okay, the initialization, data transfer, and disconnection. For initialization, the initialization can be requested by either side, okay, of the device, okay, by sending like a set mode command, like set normal response mode or set asynchronous response mode, something like that. The command is used to we use it for request initialization. We specify the mode, okay, and we will specify whether we use 3 or 7-bit sequence number. And if the other side, okay, accepts this request, it will send the unnumbered acknowledgement or UA frame back to the initiating side. Okay, after that it means that they have a connection. If the other side does not accept this request, it will send disconnect mode frame back to the initiating side. So it means that the other side does not agree, okay, to have a connection. The second phase is data transfer. Okay, in this case, both sides must begin to send IFrame. Okay, start from frame number 0, and if you use send sequence number NS, so 0 to 7 or 0 to 127, depending on the number of sequence number that we are using. NR is a receive sequence number. NR is the same as ACK number R. So N2 is ACK number 2. The third phase is disconnection. Okay, so you have initialization, data transfer, and then after you finish sending the data, communicating, then you have to disconnect. Okay, so you can either end, okay, like when you talk to someone, either end can hang up. Okay, so either end can initiate the disconnection by sending a disconnection frame. This is an unnumbered frame, DISC, and the other side must accept. Okay. If you want to hang up, okay, the other side cannot say, oh, wait, do not hang up, okay, they cannot do that. But if you want to call, then they have to accept the call, okay. So when you initiate the connection, both sides have to accept, but when A asks for connection, B has to accept. But if A wants to disconnect, B must accept, okay. Now let's look at an examples of the operation. For the first one, okay, link set up connection. In the leftmost picture, you can see that in this case we draw the space-time diagram in the vertical line, okay, instead of the horizontal line. So the time is in the vertical line. Station A and B is in a different place, okay. So A set asynchronous balance mode to B, but B didn't respond, okay, A didn't receive any response until it timed out. So A set asynchronous balance mode again, then B receive it. So B accept the connection, so B send unnumber the UA, okay. So the unnumbered acknowledgement back, okay, then it can continue transmitting the data. Now after it's done transmitting the data, A want to disconnect, so A send the U frame, disconnection frame, and B have to acknowledge, okay, with the unnumbered acknowledgement frame, and this is the disconnection. So link set up at the connection and disconnection, okay, the first example. The second example in B is the two-way data exchange, okay. In this case, you have A and B. Again, is in the vertical line. A sent IFrame. The first one is I, okay. The first one in the three values here is I, which means that it is IFrame. The second one is send sequence number. The last one is the receive sequence number. So A send the first frame. Since it's the first frame, it's frame number 0, okay? And it haven't received anything from B yet, so it's X0, which means that it's expecting frame number 0. So it's I, 0, 0. When B receives this frame, B received it correctly, so B send, and B also have data to send to A. So B also send an I-frame, and the send sequence number, this is the frame of B. So the first frame of B is frame number 0. So NS of B is 0. And the last bit is 1, because it have received frame number 0 from A correctly. So it sent ACK 1. Then, okay, then the third line, okay, is I11, because A still have data to send to B, and it get acknowledgement 1, which means that B has received frame up to frame number 0 correctly and want to receive frame number 1. So A send frame number 1, so NS is 1, and it's ACK frame number 0 that B is sending, so the last bit is 1. Because it uses sliding window, okay, so it can also send the next frame in the window, so it's also send frame number 2. Okay, still ACK 1 because it haven't received more frame from B. The fifth line here is I13 because B sent data, want to send data to A still. Okay, so it use IFrame. The last frame of B is 0, so this frame has to be 1. And because it's received ACK from A, that requesting frame number 1, so it can send frame number 1. And it's acknowledged frame X3 because it has received frame number 0, 1 true from A correctly, and it's requesting frame number 3. Okay. Then the next one, I32. A received I13, so it's know that B has received correctly up to frame number 2 and requesting frame number 3. So it sends frame number 3. And it have received frame number 1 from B, so it's acknowledged with number 2, so I32. Then B sent 2 frames, I24 and I34, because it received frame number 3 from A correctly, so it's sent ACK4, and it has sent frame number 0 and number 1 to A. Okay, so it's now sending frame number 2 to 3, 2 and 3. Then A doesn't have anything else to send, so A sent RR4, which is an S frame or supervisory frame, to acknowledge that it had received everything up to frame number 3 correctly and requesting frame number 4. Okay, so this is supervisory frame at the end. This is two-way data exchange. The third example is a BC condition. Okay, so this case, A and B communicating, okay? Suppose right now B is sending up to IFrame and frame number 3 and ACK number 0, okay? Which means that it's expecting frame number 0, okay? A is not ready to receive another frame, okay? So A send receive not ready number 4, which means that it received correctly up to frame number 3, but not ready to receive frame number 4. Now B sent receive ready 0P, okay? This means that B is has nothing else to send. Actually, it's B may have something to send, but B cannot send, okay, because A say not ready to receive, okay, so B has to send supervisory frame RR0, which means that it receive ready, so it's ready to receive frame from A, and 0 is like X0 because A haven't sent any more frames, so it's still requesting 0. And P is poll, which means that it set that bit to 1, okay? Asking A what happened, the status of A. So A say, I'm still not ready. So you send receive not ready, number 4 again, but set the bit F to 1 to tell B that this is your answer of what you are asking. I'm still not ready. In a little bit, B receive RR0 here again, okay? To ask the status of A again. Now A say, oh, okay, I'm ready. I'm ready now. So A will send RR4F, okay? Instead of RR, it send RR4F. That I'm ready to receive more frames now. Then B can send IFrame, frame number 4, and still X0. Okay. The next example is reject. Discovery, okay? This is go back and ARQ. A sent to B, information frame number 3 and X0, and then it sent number 4 and number 5. Number 4 is lost, okay? So when B got frame number 5, it's know that number 4 was lost, so it sent reject number 4 to A. So A have to resend number 4, number 5 again, number 4, number 5 again. And if it want to send more, it can send number 6 later. Like that, okay? So even though number 5 is correct, was received correctly, B will discard it because we use go back and ARQ, okay? But if you use selective reject, okay, you have to send only number 4, okay? You don't have to send number 5 again if you use selective reject. But if you use reject, mean that you use go back in, you have to resend number 4 and number 5. The last examples, okay, is timeout recovery. In this case, okay, this is to play safe, we have a timeout. So A sent to B, frame number 2 and frame number 3, but frame number 3 was lost. When B received frame number 2, it sent receive ready 3, which means requesting number 3. Then A wait for the acknowledgement of frame number 3, but it didn't receive, so it wait until timeout. So it will ask the status of frame number of B, okay? Sending receive ready 0, X0, okay? Poll, okay? So set that P bit to 1. So B send RR3F. This is your answer, okay? I'm receive ready, expecting frame number 3. So A knows that frame number 3 has something wrong, so it has to resend frame number 3 again. So it sent information frame number 3 and X0. Then B receive frame number 3 correctly. It can send receive ready number 4. Okay. So this is how you use the poll and final. Okay. This is what I just talked about. Okay. About how you use poll and final. Okay. And the abbreviation. So this is the end of chapter 6. Next time we will talk about chapter 7, which is multiplexing. Thank you.